Hi everyone, so we have been saying that the atmospheric pressure is about 100,000 Pascal. So what does the 100,000 Pascal really mean then? Okay, we know that the atmosphere consists of a lot of gas particles. You have nitrogens, oxygens, carbon dioxide, dust particles, many little particles. So how does the little particles cause such a great pressure exerted onto your body, let's say? So in this video, we are going to study gas pressure by studying the motion of particles and their collision to the wall. And we will try to relate the macroscopic pressure with the microscopic motion of the gas particles. So let's get it started. So we want to study gas pressure using kinetic molecular model. So what is kinetic molecular model? So it's a model which describes how particles, gas particles to be more specific, moves. Okay, so this kinetic molecular model provides us a lot of insights because it allows us to understand what is pressure, and after we know what is pressure, we can further relate it to temperature. So we basically, kinetic molecular model is a model that allows us to understand microscopic features or states. You call it temperature, pressure, all these things. You relate the macroscopic things to the microscopic things. So remember, kinetic molecular model, a very useful tool for us to study all this thermodynamic state. So we want to talk about pressure here, gas pressure. So what is really gas pressure? So we probably learned from previous lessons that pressure is perpendicular force per unit area. So if your area is like this, then when you exert a force on it, amount of perpendicular force to this surface per unit area. So that probably a force is being exerted over an area. So you find the perpendicular component and you divide it by the area to find the perpendicular force per unit area, and that's what we call pressure. So how does it work for this gas pressure case? So let's say we have a gas container. We usually in kinetic molecular model, we assume there's a container, a big container. Inside there's a lot of gas particles. So the gas particles will constantly collide with each other or collide with the wall. So when it collides with the wall, what happens is it will impart a force, okay, or it will exert a force on the wall. Okay, so let's say it exert a force like this. So this is the force exerted by one gas particle on the wall. Okay, but of course a gas container doesn't just contain one gas particle. It contains a lot, plenty of gas particles. So what happens is there's many particles colliding with the wall at every single time. Okay, so there can be particles colliding here, colliding there, many particles colliding. So each of those particles will exert force on the wall of the container. So if you are able to find the force exerted by one single particle and you multiply it by all the particles that is colliding on this unit area of the container, if you divide it by the area, the force exerted by the particles on the wall, you divide by the area of the container, you are able to get the pressure exerted by the gas particles on the wall of the container. So this is a sort of a rough idea what we are going to do. So we are going to find force, then you divide by the area of the wall. How do you find force? We use back something we learned in impulse and momentum, which is change in momentum of this, in this case the gas particles, change in momentum of the gas particles. If you know what's the time frame of it, you can convert it to the force exerted by the gas particles on the gas container wall. So since we say we want to talk about momentum first, so our first step will be to find the momentum. Okay, so let me write it down first. We want to find a change of momentum. So how are we going to find this change of particle when a gas particle collides with the wall? How we are going to do this is we are going to recall our impulse momentum theorem. So let me draw a simple diagram to illustrate this thing. So you have a gas container wall and you have a particle. So let's say this particle now is traveling to the left. So if it's traveling to the left, I will probably call this as negative magnitude of velocity. And since it's in the x direction, I will call it v in the component of x. Okay, so this modulus stands for speed and negative stands for it's going in the negative direction, and x means by it's in the x component here. Okay, so using our knowledge of momentum, we know that if it's an elastic collision, which comes from the assumption of kinetic molecular model, every collision must be elastic. So if we know it's elastic, then it conserves kinetic energy, so the velocity that returns after the collision should be having the same magnitude as before. To know more about this, you should check the prerequisite video that is posted now. Okay, so we will have the we have the velocity in the opposite direction. So it's appropriate that we call it as Vx, but now in positive. So after we know this, okay, let's add on a little bit of detail. The mass of this gas particle is m. So knowing that, we are able to find the change of particle, which is delta change of particle. Change of momentum, which is delta p. Delta p is equals to p final minus p initial. Just little thing to be careful about. This momentum here, it's denoted using capital P in this situation. Okay, because later we are going to use small p to represent pressure. Okay, so knowing that, we can write down stuff. We know that pressure is just mass times velocity. So final, it's positive, so it's mvx. Initial, it was negative vx. So if we combine the stuff together, it becomes 2mvx. So this is the change of momentum of one gas particle when it collides with the wall. So after we know this, what we need to know is we want to find how many particles are colliding with the wall over within a period of time. Knowing that, we are able to find the total change of momentum of the gas particles when they collide with the wall. We find one particle, how much change momentum. Now we find how many particles, so we can find the total momentum. Okay, so let me write down the second steps. So now we are going to study how many gas particles collide with the wall within time delta t. So we fix our time period, our duration here to be delta t. So we want to find how many gas particles is colliding with the wall within this duration of time. So to do this explanation, it requires me to bring in a gas container. So give me some time to draw a gas container. Okay, so now we have here a gas container containing particles inside. Okay, so these are gas particles and they are bouncing around random motion, colliding with each other, colliding with the wall of the container. So the first step that we're going to do is we're going to simplify the situation to make it manageable for us to do some derivation. So the first thing that we are going to simplify is we are going to ignore we have three dimensions of motions right now. Things can move either upwards or downwards, at the same time leftward or rightward, or it can move to the front or to the back. So there's 1, 2, 3 dimensions right now. So 3 dimensions, analyzing 3 dimensions is really quite hard to follow. You will need matrices to do it. So the thing that we should do right now is to ignore the other 2 dimensions. Focus on only one single dimension, and we choose that dimension to be x. Okay, all the dimensions should be equivalent, because if you change what the box from this orientation, you rotate the box to look like this, the gas pressure won't change. So that means by whether you are using the x wall, the left right wall, or you're using the up down wall, or you're using the front back wall, it won't change anything. Because we don't care about gravity. Gravity is negligible in this case. So up, down, left, right, front, back doesn't really count. Okay, so let's just remove the two dimensions first. Okay, let's remove the front, back dimension first. So give me some time, I'll be back. Okay, so now we have simplified things to be in two dimensions. So now if you represent any velocity, the velocity should probably look something like this. So if this thing is moving, this gas particle here is moving in this direction, what it actually means is there will be two components. One which is going upwards, which is Vy. Another one will be going leftward, which is Vx. But again, I say two dimension is still too much. We want to reduce it to one single dimension. So let's break it down further. So we want to remove the up and down, the top and bottom wall, because we focus on the left right wall. Okay, so if further we do remove another dimension. Okay, so that's what we end up with. So we only focus on the x direction, so all the particles can be moving to the left or to the right. So let me write down what we have done here. Okay, the first step is we reduce it to one dimension, one direction only. Okay, so now the next step that we are going to do is to acknowledge something. Okay, so the next thing that we are going to acknowledge is all the particles here are moving. Okay, so some particles will be moving to the left, some particles will be moving to the right. So let's say this one is moving to the right, and probably some of this is moving to the left. Okay, now we have another one here moving to the left. Okay, so particles can, if we are focusing on the x direction, particles can either be going to the left or going to the right. Okay, we're focusing on one single dimension only, the x dimension. So things can be either moving to the left or moving to the right. So how many particles are moving to the left? How many particles are moving to the right? So this can be a complicated situation to analyze, but again, kinetic molecular model, we assume the particles to be moving randomly. It should be in random motion. So if it's in random motion, it should not be biased. Okay, this means that a gas particle has the same probability of going to the left and has the same probability of going to the right. It's an equal chance of either going to the left or going to the right. So in that case, if we have many particles, what we can do is we assume half of the particles are going to the left and half of the particles are going to the right. So that's the assumption that we are going to make. So let me write it down again. Okay, so what we are saying here is half of the particles are moving to the left, half of the particles are moving to the right. So there should be half of the total amount of particles going to the left, half of the total amount of particles going to the right. So that's the assumption that we make because we assume that the motion of gas particles is random. So if we look at this simple diagram here, you can see I have two arrows pointing to the left, two arrows here pointing to the left, and I have two arrows here pointing to the right. Just a rough representation. Okay, so what's the purpose of saying this? Because we want to further simplify the situation. Just now we say a gas the gas container has 6 faces. So you have your up down face, you have your front back face, you have your left right face. So what happened is just now through the first step we resolve a V and we ignore the other two dimensions. We essentially remove the top bottom wall and we remove the front back wall. Now we assume that half of the particles are going to the left, half of the particles are going to the right. So means by those particles that are going to the left, they will collide with the left wall. If the particles are going to the right, then they will collide with the right wall. So what we do now is we want to further simplify by removing one of the wall. So what do we mean by removing one of the wall? Means by we are ignoring all the particles that are moving to the right. We only consider the particles that are moving to the left. So we are making the situation really simplified because we want to focus on one single face on the container only. So we want to focus on the left face in this case. So how do we remove all the particles? How do we ignore all the particles that are moving to the right? We only take into account half of the total number of particles, because that's the number of particles that are going to the left. So we take half of the total number of particles. That's why later you will see a factor of half being introduced into the equation later. So let me write down a big half over here. Okay, so now what's our next step? So let me write down C first. The next step is we want to simplify the situation again. So what's the simplification that we're going to do? Well, particles can be moving fast, it can be moving slow. Besides that, the particles can be moving in direction that if you reach for the component of x is small. Okay, if you like compare it between these two situations, you can have particles moving like this. In that case, if you resolve it, the amount of v in the x direction will be this small. Whereas, if you take another particle which is really moving like this, then you will see that this will also be v in the x component, x dimension as well. So if you resolve the velocity components, all of them, you resolve the gas particles to x direction, you'll see that some will have more speed, greater speed in the x direction, some will have less or smaller speed in the x direction. So it's a spectrum. You have something moving at high speed to the left, you have something with low speed moving to the left, a range of speed. So the next simplification that we're going to do is we want to assume all the particles are moving towards the left wall with the same speed. Okay, this is a weird assumption, but we are going to assume they are the same speed. You might be thinking this is an absurd thing to make. How is it possible for them to all be at the same speed? Well, we don't really care actually, because if you want to consider all the different velocity, you need to do integration and stuff will be blown out of scale. It's not within our range to do so. So what we do is we make everything the same speed, and later we will use an average to replace this assumption that we make. Okay, the average idea will be used later. So let me write down what we will do now. Okay, after making that assumptions, I think we have already done all the assumptions that we need already. So don't worry, we have go through three things of simplification. The first simplification is we remove all the other faces, the top bottom wall, we remove the front back wall, leaving left and right wall. Then using the assumption that half of them is moving to the left, half of them moving to the right, we remove the right wall by focusing on only half of the total number of particles. So the third thing that we are assuming here is we assume all the particles, the gas particles here, are moving with the same speed, which we call it as modulus of Vx. So we have done a lot of simplification. Time to really go and find out how many gas particles are colliding with the wall within time delta t. Let me solve the r here. Okay, so let's keep it going. How do we determine this? So if all of the particles here are moving with the same speed, so if we only specify a specific duration, let's say 0.5 seconds, let's say, okay, then all the particles would have traveled the same distance in the x direction within that 0.5 seconds, because all of them have the same speed in the x direction. Therefore, if we fix a time duration, let's say you want to see how much distance has traveled by all the particles in the x direction within 0.5 seconds, you see that all the particles will have traveled the same amount of distance in the x direction. Because if the speed of all of them is the same, if the time that we want to investigate is fixed, v and t is fixed, of course the product of it, the distance, will be fixed as well. So that's what we are going to assume. So knowing that they have the same distance, So what we are going to do now is, let me write down this thing first. Probably explaining it with words written down will be better, because this is slightly complicated. Okay, so it says here, within time delta t, if you want to hit the wall, the U is, if a gas particles want to hit the wall, the gas particles have to be within the distance of Vx times t from the wall. Okay, the Vx here is the speed of the particles in the x direction, the delta t is the specified time. So if you multiply these two things together, you get a distance. So what does this mean? So let me draw something. Okay, let's say in a specific time, in a specified time, we assume that all the since they are all moving in the same speed, we see that all of the particles here, we have traveled this much distance, and this much distance is d, which is Vx times delta t. Okay, so which particles here would have hit the wall? Let's try to find it out. So if a particle is near the wall, you have seen that the distance traveled have already touched the wall. So means by this particle that I put my arrow here would have already reflected off the wall at quite early stages. If the particle is slightly far away like this, at the end of this time delta t, it will just touch the wall, touch the wall. But if you see these particles is even further away than this point, then you will see that these particles within the time delta t would not have reached the left wall. So if you see here, particles have to be within a certain distance away from the wall, only they are able to touch the wall. And this distance, as you can see, I'll use pink. Oops. No. Okay, I'll use pink. So this is the distance where if the particles are within this area of the wall, if you are within this area of the wall, within this distance from the wall, sorry. If you are within this distance of the wall, the particles will hit the wall. Okay, I'm assuming all the particles are moving to the left, based on the assumption that I make in B. Okay, I'm only talking about the half of the total particles. So all these particles are moving to the left, but only particles in this region here will hit the wall. Particles on the other side here will not hit the wall. Okay, so if we are able to find how many particles are there in this pink region here, in this hit the wall region, then that's the number of gas particles that will collide with the wall within time delta t. So our mission here will be to find how many particles are in this region here. So how to find? Well, I don't think you'll be thinking that it's just by counting this diagram, right? No, okay, not that easy. So we are going to figure out a formula for us to find the number of particles that are within this region. So how do we find that? Let me scroll down a little bit. Okay, so what we will do, okay, let me write down in here. Okay, let me write down the sentence first before I explain. Okay, so now we'll be finding the number of gas particles that collide with the wall within this time delta t. So how do you find this? We know we have already specified this pink region to be the volume, where if you're staying in this volume, you'll be able to hit the particles. If you're outside of this pink volume, you are not able to hit the particles. So what we are going to do now is taking the volume that is possible to hit the wall. Okay, I'm just writing in terms that you can understand. Volume that is possible, and you divide it with the total volume. So taking this possible volume divided by the total volume, essentially you are finding the ratio of possible divided by total. Okay, so you are finding what is the portion of the gas particles that are able to hit the wall. So now what you need to multiply is with the total number of particles. So you are finding the proportion of particles that are able to collide with the left wall. Total number of gas particles. So how do we fix all these components out? So the volume that is possible, how do we find it? We know that the distance here is Vx delta T. And we know that this wall here would have an area. Okay, this wall is a wall in 2D, but you know this is actually a 2D wall. So this wall here would actually have an area. So the area of this wall will be A. So area times length, that will be volume. So this will be the volume that is possible for the particles to hit the wall. So volume that is possible, how do you write it? You can write it as A times Vx times delta T. Okay, so that is the volume, the pink volume in this diagram. And we divide it by the total volume, capital V. And we times the total number of gas particles. But remember, this total number of gas particles, we only want those that are moving to the left. Okay, because if you are moving to the right, it will definitely be impossible for you to touch the left wall. So these are all particles that are moving to the left. That's why it's the total number of gas particles, but you divide it by 2 or times with half, because you only want half of the gas particles, because that's how many gas particles that are moving to the left wall right now. So taking this total number of gas particles, you multiply by the pink volume divided by the total volume, you are able to find the proportion. Okay, this proportion times the total, you find the number of particles that will be colliding with the left wall right now. So let me rearrange this equation a bit. So this equation will be half A Vx delta T times N over V. Okay, so with that said, we have find the total number of gas particles that will be colliding with the left wall within this time delta T. So let's move on to the next section where we discuss how to merge this thing with the change of momentum that we find much earlier just now. So let me zoom things out a little bit. So we have find two things right now. The first thing that we find is the change of momentum of a gas particle when it collides with the wall. And then we find the total number of particles that will be colliding with the left wall. So if we multiply these two things together, we are able to find the total change of momentum of all the particles that are colliding with the left wall within time delta T. So let's write down what we'll be connecting these two things to. Okay, let me draw the connection. You connect between this thing and this thing here. Okay, so we are going to find the total change of momentum, and we know it's the multiplication of change of momentum of one particle with the total number of particles that are colliding within this time delta T. So let's write down in words that we can understand first. Okay, so it will be the number of gas particles that collide with the wall within time delta T, which is essentially this thing that we got down here. And we will multiply it with how much change of momentum for each of the gas particles, which is something that we find up here in section 1. So let's just multiply these two things together. So it will be half times A Vx delta T and V, then multiply it with 2mVx. So if you multiply these two things together, what you get is the half and the 2 will cancel to become 1. And what's interesting is there's 2Vx here, so you get Vx squared. So let me write down what's the combination. Well, it's a very long equation, probably the longest string of symbols that you've seen in physics for now. How many symbols are there? 7 symbols in one single equation. Okay, that's quite complicated, but there's a little bit of things that I want to fix here. Have you seen that there's a modulus and there's a square here? So we know that if something is being squared, the value can never be negative. So it's essentially what I'm trying to say is you can remove the modulus sign right now. Because squaring something, you end up with a positive value. So there's no need for modulus anymore. So this is the equation for the total change of momentum within time delta t. So let's call this delta P total. Okay, so having this total change of momentum, what we will do now is we will want to relate it to the force that we have mentioned at the start of this video. We want to change of momentum to be force. And the way to do that is to recall your impulse momentum theorem. If you have no idea what's impulse momentum theorem, it's better that you review the prerequisite video where we explain impulse momentum in greater depth. Okay, so the fourth step, let me write it down first. Okay, so we are going to go from change of momentum to average force. The theorem we use, impulse momentum theorem. So let's just write down this impulse momentum theorem first. It's a very important concept, so let's use the yellow. So J equals to the change of momentum, and since we are talking about the total change in momentum, let's just be careful and write down total. Okay, so what we are going to do next, we have to know that this impulse here is just, if we do it in the average way, it will be the average force times the duration of this force being exerted. So this duration here is exactly the same as the duration that we mentioned in situation 2 here, not situation 2. The steps number 2 that we have just now. The duration where we look for particles colliding at the left wall. So that's the exact duration that we are going to talk about. So let's continue and fit in everything that we have from step 3. So I believe what you can see here is impulse momentum theorem with a little chance of doing some simplification. Okay, we see delta t on both sides of the equation, so I can do eliminate them. Eliminate the delta t. So now we have found our average force to be m n a vx squared over v. Okay, so let's do a bit of recall what all of this formula means, because we have gone through a long way. So this m here represents the mass of one single gas particles. The n here represents the total number of gas particles in the container. The a represents the area of the left wall. Then this vx here represents the speed. Okay, it's been squared already, so velocity and speed doesn't really care anymore. It's the speed of the gas particles. Okay, we assume that they are all the same. The speed of all the gas particles in the x direction. Then the v here is just the volume of the container. So now after getting the average force, we are very near to our last aim. Remember our aim. Our aim here is to get gas pressure. We want to get gas pressure. So from force to pressure is just one step left. Now it's just dividing it with the cross-sectional area. Not cross-sectional area, dividing it with the area of the left wall. So how do we find this pressure exerted on the wall? Again, it's perpendicular force per unit area, and since all these particles, we assume they are moving in the left direction only, so the collision will be a perpendicular to the wall. The collision will be perpendicular to the wall, so the force exerted will also be perpendicular to the wall. So now we don't need to care about components to the y, components to the x. We focus everything in the perpendicular component. So no resolving to do here. It's just a plain O F divided by A. So pressure, we use small p here. Will be F in the x direction divided by the A of the left wall. So that will be M N A V x squared over V, then divide by A, write A here. So now something can conveniently be crossed out. So you end up with your equation being mn Vx squared over the volume of the container. So that's a really long differentiation, but we have ended up with something. We are relating the pressure experienced by the wall, we are relating it to the velocity of the particles. This is something really elegant because it shows P. P is something that you can measure. It's a macroscopic properties. It's the pressure being experienced by the wall. But Vx here is representing little particles colliding with the wall. So essentially, you are relating something really humongous with something really tiny, both in one single equation. Really elegant. So the last step that we are going to do is we want to generalize this. We want to break away the assumption of things being fixed in one dimension. Break away the assumption and make it a general equation for pressure. So that's our step 6. So now we are going to generalize this equation, which is previously in x direction only. We are going to generalize it back into 3-dimensional velocity. So to do that, first we have to do something first. We previously put an assumption that the Vx, all of them are the same. All of the particles moving to the left are having the same speed. Well, previously it sounds absurd, okay, now it still sounds absurd. So what we are going to do is we are going to take off this assumption. How are we going to take off this assumption? Well, if you really want to do it properly, what we should do is we should categorize the low speed particles together, the medium speed particles together, the high speed particles together, so probably a few groups. You calculate the force exerted by each different group of particles, then slowly you add them up together to form the total change of momentum, then you find the total force, then you find the pressure. But that would be too long-winded to be discussed, and there's not much insight you can get from doing all this long-winded calculation. So one simple thing we can do is through the idea of average. We are taking an average of the velocity to the x direction, taking an average of it to represent the whole situation. Using an average to represent the two extremes, bringing it back to the middle, the average. So that's what we are going to do. So to do that, first we change this thing to average. So P is now mn Vx squared over V. So if you want to make it into average form, so what we will do is we just attach an average at the bottom. Previously it was a fixed speed, but now we take this fixed speed to be the average. speed. Therefore, we can substitute the average x direction speed to replace Vx. So now, after doing this average thing, we should try to find out how to make it back into 3D. So if something wants to be 3D, let's find how do you represent velocity in terms of their components first. So velocity is v. Okay, if you want to find the magnitude of that velocity, then it will be the component in x plus the component in y plus the component in z. That is how you get the magnitude of the velocity of all the particles. Okay, all the particles, if you want to find their velocity, the magnitude of velocity, which is speed, what you can do is you take the x component square plus the y component square plus the z component or z component square, then you put them together, sum them up together, put a square root, then that will be the magnitude of the velocity of that gas particle itself. So we say you want to take an average approach to study this thing. So to take an average approach, what we will do is we will make everything to be average. Okay, now after making everything into average, next thing that we are going to understand is, just now, if you remember, I say if you have a gas container, turning your gas container like this, turning your gas container like this, turning your gas container like this would not make any difference with the gas pressure. Just now we picked the left wall to study, right? If you don't like left wall, you want to change it to the right wall, you still get the same equation out. Okay, it will still be exactly the same equation. Even if you want to change it to the top wall, what you will get is just Vy squared instead of Vx squared. You still get the same equation come out, because there's no laws of physics that tell you in the x direction you must move more compared to the y direction. Y direction must be moving slower, x direction must be moving faster. There's no such thing. All the dimensions, they are just directions. Okay, so if the x direction has this amount as average, the y direction should have the same value as its average. Same for the z average. So what I'm trying to say is Vx average should have Vx average square should have the same value as Vy average square, and it should also have the same value as Vz average square. So all these three things that I have highlighted should be the same value, because there's no bias in which direction should move faster or which direction should move slower. There's no this kind of speed bias. Okay, so if they are essentially the same, what we can do is we can change it, all of them, to become in terms of x. Okay, because you might see where we are heading to. So this will essentially be another x. This will be essentially another x as well. Why do we do this? Because now we can add these three terms up together. So now it will be 3vx AV square equals to AV. VAV. So the average speed right now is 3 times the average speed in the x direction, and 3 times the speed of the 3 times the speed in the x direction. So now what we could do here is do a bit of square, then you become VAV square, then you become 3vx AV square. Now I hope you see where we are going with. We change Vx AV square as our subject, then it will be 1 over 3 VAV square. So what's the purpose of doing this? Because we want to replace the Vx average, we replace it, highlight the square as well, we replace it in terms of the actual average speed of the particles itself. So if you want to do this replacement, what will be the final equation? The final equation will be P equals to mn times 1 over 3 VAV square divided by V, which if I rearrange a bit, it will be 1 over 3 mn VAV square divided by V. V is the total volume. So if you want to match it to our syllabus say V average square. V average, we call it as the root mean square speed. So if you want to change it to root mean square, that will be 1 over 3 mn, then you have this symbol here, square over V. Okay, root mean square means by you square something, then you find the average of the square, then you square it back. Okay, let me write this as an extra thing. So the idea of root mean square is, what you want to do is you have something, let's say Vx. Vx, we say there's an equal amount of particles moving to the left and an equal amount of particles moving to the right? So if we average up together, the big left and the big right will cancel each other out. The small left and the small right will cancel each other out. So essentially, if you average out all the x direction velocity, the answer will become 0. So the actual Vx average will become 0. So 0 is meaningless for us. So what we do here is we get the average of the square. Okay, so we square it up. Then after that, we sum all the individual square of velocity. We sum all the individual speed square. So after we sum them up, what do? We square root the answer back. We square root all the answer back. Okay, you sum and you average. Okay, let me get this clear. You have a lot of particles, then all the particles have different velocity in the x direction. So what you do is you get the velocity in the x direction, you square it, so everything will be positive. So if everything is positive, you sum them up, you will not cancel out the 0. Before this, there's negative velocity, there's positive velocity. So if you sum them up, you go back to 0. So now you square them to make everything positive, you sum them up, divided by the total number of molecules, then you get an average. So after you get the average, only you square root it back. So that's why this is what we call root mean square. So you have the square first, you square first, then you sum them up, then you find the mean. After you find the mean, you square root it back. Okay, so that's the idea of root mean square. And after you do this root mean square, you find this thing to be Vx. Okay, so for our case, it's V square, then it becomes equals to V. Okay, this square root and square should come together, because if you cancel each other out, there's no meaning. Root mean square comes from you square, then you find the mean, you find the average, then you square root it back. That's the idea of root mean square. That's why this equation now, okay, this equation now is P equals to 1 over 3 mn V square over V. Okay, the V square here is root mean speed square over V. So we have gone through a long way and we are able to arrive at this final equation. So let me zoom all this thing out to have a bigger picture. So this is what we have done throughout this whole video. So what we'll do in the next video is we'll try to unpack this equation. We'll try to see what this equation means. And after knowing how this equation works, what does this equation mean? We try to make a further step by relating this thing, the V here, we relate it to kinetic energy. The root mean speed here, we relate it to kinetic energy. Then going further than that, we relate it to temperature. So we are trying to bind more macroscopic observable properties with more of the microscopic motion of particles. That's our purpose for this series of video, and this is our purpose of this chapter. So stay tuned for the next video.